Okay, there we go. So, recording is started. Let me go ahead and share the screen, and then let me know if you guys can see that well. Looking good? You guys can see the problem? Yes, okay, awesome. So, yeah, this week's stuff is the waves, oscillations. This is written homework week 14. There's a little bit of a throwback to energy stuff somewhere like throughout this chapter. I think it's towards the end of the slides, but yeah, a little bit of a throwback to energy, but very, very like basic concepts of energy, just using the equations to manipulate them and try to get certain like energy values converting between potential and kinetic energy. So hopefully nothing too bad. But yeah, let's go ahead and get started. So problem 1 is mass on a spring. So it says we have a 2 kilogram mass attached to a spring with spring constant 200 newtons per meter. It oscillates on a horizontal frictional surface. Now the total energy in the oscillator is 0.25 joules, and the equilibrium position is at x equals 0. So we have mass is 2 kilograms, right? Spring constant is 200 newtons per meter. Cool. We have the total energy, E total, is 0.25 joules, right? And then equilibrium position is x equals 0. So the equilibrium position is something that we're going to be talking about here later in some of the steps of the problem, or in other like problems here, whether it be problem 2 or problem 3. Equilibrium position is very important to understand, especially with how it relates to what type or how much energy you have at your specific like compression or extension distances. So we'll talk about that when we get to the energy parts of these problems. That's the information that's given to us so far. Now part A is asking us to determine the angular frequency of the oscillator. Now angular frequency, we've seen that term before. It was one of the older chapters with circular rotational motion, right? We did that kind of, I don't know if it was the same week as torque or like a week after, a week before, but around that range. So angular frequency, if you remember, is omega, right? I don't know if I shared with you guys that I like to call it fancy W because it just looks like a fancy W, and it's a fun, nice, easy way to like make physics, I guess, a little bit more lighthearted and I guess easier to remember. So if you think fancy W, yeah, that's angular frequency, right? Instead of like saying, oh, omega, whatever, right? Anyway, but angular frequency is fancy W. That's 2 pi f. F is frequency, and that's the same as 2 pi over period, which is t, right? So remember, frequency is how many cycles we're going through per second, and then period is the amount of time, so the amount of seconds, right, or number of seconds it takes us to cover one cycle, right? So frequency is the number of cycles per second. So if you have like something going at like 3600 hertz, okay, that's 3600 cycles per second, right? Hertz is inverse seconds, or seconds to the -1 power, right? So if I say 3600 hertz, that's 3600 cycles per second, or revolutions per second, revolutions per minute as well. Those are units of frequency. Period will just be in seconds, and that'll just tell you the amount of time it takes to cover one cycle. So that's just kind of a refresh of what angular frequency is, right? Now, there is another equation, right, for angular frequency, and that's introduced to us in this chapter, which is omega is equal to what? Does anyone remember what that other equation is? Exactly, yep, excellent. Good job. So we have the square root of the spring constant divided by the mass. That's the other equation that we have for omega here, our angular frequency, right? Introduced to us in this chapter. So if we want to find out the angular frequency, we'll have to look at, can we use this equation, or that equation, right? So we don't have information about frequency, we don't have information really about period, but we do have the spring constant and we have the mass, right? So it's very simple to figure this out. We can just take omega is equal to square root of that 200 newtons per meter for that spring constant divided by 2 kilograms, right? So that gives us a square root of 100, right? Newtons per meter divided by kilograms. You can cancel out the units if you want, but yeah, go ahead. Oh, I'm frozen. Oh, shoot. Okay. 1 second. Thank you. There we go. Is that better? Awesome. So you have root 100. You can cancel out the units if you want to and try to figure out what the units are, but it's not like worth like looking at what the units are and how they cancel out, because newtons is kilograms times meters per second squared, and there's a whole issue that you have to go through when you're canceling out the units. But essentially you'll just get at the end that square root of 100 is 10, and angular frequency is measured in units of radians per second. So 10 radians per second, right? That's our angular frequency there. So that's the angular frequency for part A. Now part B is asking us about the amplitude of the oscillation, right? The amplitude of the oscillation. So remember, amplitude A, that's going to be the maximum distance that you can compress the spring or stretch the spring. That's the amplitude, or that's the definition of the amplitude, right? Now, how can we relate amplitude, right, to other pieces of information given to us, right? So we have total energy, for example, that's 0.25 joules. We have that angular frequency value that we figured out. Can we use either of those two values to figure out the amplitude? Is there a relationship between energy and amplitude, or is there a relationship between angular frequency and amplitude? How can we figure out the amplitude of the oscillation here? Any takers? Yep, excellent job, Kimberly. Yep. So we have E total energy, that's going to equal half Ka squared, right? So amplitude squared times our spring constant times 1/2 is going to give us our total energy. Well, we have our total energy already, right? That's 0.25 joules, so that's awesome. So we can take 0.25 joules is equal to 1/2, and then times our spring constant, 200 newtons per meter, and then we can just solve for A, right? So, yeah, am I frozen again? All right, 1 second. And there we go. So yeah, we have our total energy is equal to 1/2 times 200 newtons per meter times our amplitude squared, right? So if we go ahead and solve for that, we should get an amplitude of, I think, 0.05 meters, right? Let me double check that, and go ahead and double check it as well with me. Yep. That would be the way to figure this out. Yep. You relate your amplitude that you're figuring out to another value that we have given to us. And so, for example, we have that total energy, right? And so you have total energy, you know the total energy is equal to 1/2 times your spring constant times your amplitude squared. Yep, that's actually the exact same idea, same equation there, right? So elastic potential energy is equal to 1/2 K delta X squared. However, in this case, right, it's actually literally the exact same thing. It's just that when you write UEL, right, that's your energy, elastic potential energy, half kx squared. This can be used to figure out the elastic potential energy at any stage of the process, right, of compressing or stretching the string. However, when we use E total is equal to half Ka squared, well, the amplitude is the maximum distance that you can stretch or compress the spring, right? So if I stretch it 0.05 meters, right, that's the maximum distance I can stretch it. I literally cannot stretch it to 0.05000001 meters, for example. I cannot stretch it beyond this point. So at that point, while it's stretched, right, there's that maximum stretch, and so there's no motion either, right? There's no motion, so there's no kinetic energy. So at that specific distance, that maximum distance of compression or stretching, I will be completely stretched, completely compressed, with no motion, no kinetic energy, and all of it going to elastic potential energy, right? So when we say E total, we're referring to the fact that at that maximum compression or stretching distance, which is defined as the amplitude, right? A right here is also x, right? It's a certain distance away, certain x distance away, or certain y distance away, for example, if you were hanging the block on a spring, right? It's just that A, the amplitude, is defined as the maximum x distance or y distance, right, that you can stretch or compress a string by. And so at that maximum distance that you're compressing or stretching, there will be no motion to the block or to the spring system whatsoever. All of the energy, the E total, the total energy, will be spring potential energy. None of it will be kinetic. However, anywhere in between those maximum stretching or compressing distances, those between the amplitudes, right? Because if you're stretching, right, if you have this spring, there's the block. If you stretch it this way, you're going along the positive x distance. If you're compressing it this way, you're going to the negative x distance. So that's why you see, like on a graph, right? Well, here, if we were saying this is 0 here, right? This is your amplitude here, right? This is your maximum distance away in the positive direction. So this might be that 0.05 meters. And below here is that maximum distance again, just when you're compressing. Oh, am I frozen again? Hold up. All right. I was drawing a graph, but basically I'm saying, like, if you have a graph like this, here's your maximum distance away, your amplitude, your A. That might be 0.05 meters. That's positive 0.05 meters. You're going in the positive x direction. And then below here, it's your amplitude again, but it's negative 0.05 meters, right? So anywhere along those two amplitudes there, right? Here, there, whatever, right? You're going to have some potential, some spring potential energy, and some kinetic energy, right? But at the amplitudes themselves, it's all going to be spring potential. At that maximum compression or stretching distance, it's all going to be spring potential energy, no kinetic. And that's why we refer to the equation as E total, because that'll be the only type of energy. The total energy is all spring potential. And at that maximum distance, that x max, right? Right? If we were to plug in x is equal to 0.05, well, instead of referring to it as x anymore, we're referring to it as the amplitude instead. So A is literally the same as x. It's just like the x max, basically. Does that make sense, Matthew? Okay, awesome. That makes sense for everyone else as well? Equilibrium is not at the top there. So equilibrium would actually be like this. If this was like 0 meters and this is 0.05 and this is negative 0.05, your equilibrium point is like everywhere here at that horizontal axis, right? That's where you have x equals 0, or like delta x equals 0, right? Because then you wouldn't have any change in the springs. Like you wouldn't be compressing it and you wouldn't be stretching it. Yeah. So at the top, at the peaks, at these extrema, the minimums and the maximums, right? You're going to have all of your energy be devoted to spring potential energy, right? But then here at that equilibrium position, so imagine if I stretched this block all the way to 0.05 meters and then I let it go. So from 0.05 all the way down here, right? So if I stretch it from 0.05 and I let it go and it moves back, once it hits that equilibrium position of 0, well, if I look at the equation of half kx squared, if x is 0, what does that mean for my spring potential energy? Exactly. So there would be 0 spring potential energy at the equilibrium position because they're not stretching and not compressing. But then all of that total energy at the top had to then be converted into kinetic energy. So when you're at equilibrium position, I tried to do an at sign, my bad. At equilibrium, it's all kinetic, right? You'll have maximum kinetic energy basically. At peaks, it's all potential. So when you're maximally stretching or compressing, it's all potential. And then once you hit the equilibrium position, because that'll be the point where, like, if you're compressing a lot and then you let go, once it hits that 0 point, it's technically not stretched or compressed, but it's moving at a very fast pace, right? And so that's also where you're having your maximum velocity or maximum speed. Make sense? Exactly. Yep. Yep. Yeah. Hopefully that, like, relationship between, like, the graph and the energies, like, made sense there, because at the peaks it's all potential. At the equilibrium position, like at x equals 0, then you would have all kinetic, 0 potential, because at that point, when we're looking at half kx squared, x is 0 at the equilibrium position, so there's no spring potential energy anymore. But if you had started out stretching the block or the spring, or compressing it and then you let go, well, you started off with a total energy of 0.25, for example. That energy is conserved, and so that 0.25, remember, like, where I was talking about the energy stuff a couple weeks ago, fair few weeks ago. But that 0.25 is essentially going to be converted, going to be output from the spring potential energy and put into kinetic, basically. So it's kind of like you just suck it out from spring potential energy when you're stretched or compressed, and it's sucked into kinetic at that equilibrium position to a maximum kinetic energy at equilibrium position. So max kinetic at equilibrium, and then max spring potential at peaks or at amplitudes, basically, because your peaks will be your amplitudes. But yeah. Now, for part C, when they're asking us to determine the speed of the mass when it passes equilibrium position, right? Well, remember what I said about being at equilibrium position. What is our kinetic energy at that point? Or at least, at equilibrium position, is the kinetic energy 0? Yeah, the spring potential is 0 at that point, right? So if we're looking at, like, E total, and let's say at equilibrium, so E total at equilibrium, it's going to be made up of only kinetic, and the potential is going to be 0, right? Because at equilibrium position, x equals 0, then half kx squared, x equals 0, you wouldn't have any spring potential energy. Am I frozen again? All right. Sec. So at x equals 0, it's all going to be kinetic and no spring potential energy. So, with that being said, at that point, at equilibrium, what is our E total then? Or what is our kinetic energy equal to? Yep, so 1/2 times mv squared, right? So 1/2 times mass times velocity squared. At the same time, right, your energy at equilibrium, right? So we're trying to figure out our speed, right? We have our mass and we're looking for speed. Well, what is the kinetic energy value? Like in joules, what would E total at equilibrium be? So if you want to set this equal, if you want to set 1/2 mv squared equal to a certain value, a certain joule amount, what would that be? Exactly. Exactly, right? So if we started off with 0.25 joules, the total energy, right? That total energy is found at the amplitude, at the peaks, right? So if at that peak, if here at the amplitude we have 0.25 joules, we must have 0.25 joules everywhere along the graph, basically. The thing is, the way we have it will differ. By that I mean, what forms of energy is going to make up that 0.25 joules. So at the amplitude, like I said, it's going to be all, at the peaks, it's going to be all spring potential energy. At equilibrium, where x is equal to 0, right, at this horizontal x-axis here, at equilibrium, x equals 0, it's going to be 100% kinetic energy, 0% spring potential. So here it is, well, I don't want to write here, but at the peaks, it's going to be 100% spring potential energy or elastic potential energy. And then here is going to be 100% kinetic energy, right? So 0.25 joules, my total energy is going to be 0.25 joules of spring potential energy. Here, I'm going to have that same 0.25 joules, right? But now 100% of it is kinetic energy. So instead of having 0.25 joules of elastic potential energy or spring potential energy, I'm going to have 0.25 joules of kinetic energy at equilibrium. So we set this equation here equal to 0.25, right? Now, if I were to choose a point here, for example, I might at this point have like 0.15 joules of spring potential energy and 0.10 joules of kinetic, where if you add them up, you get 0.25, right? It's just like different flavors of energy that we can add up, basically, in different values and different amounts that we can add up to get that total energy. We know that total energy of the whole entire system will be entirely spring potential energy at the amplitude, and it'll be entirely kinetic energy at the equilibrium position. So whatever energy you have, right? Say if we were just given half and we were given the spring constant times 200, and then we had the amplitude. So they told us the amplitude was like 10 meters or something. So we calculate out what the total energy is, right? That gives us, let's say, for example, 100 joules is the total energy, theoretically, right? If we said that total energy is 100 joules, well, I have to have 100 joules at every single stage of compression, stretching, all of that. I always have to have 100 joules, right? The way I get 100 joules is going to differ based on how much I'm compressing, how much I'm stretching, and what I'm doing, right? So if I'm stretching all the way to the amplitude, or if I'm compressing all the way to the amplitude, I'm going to have 100 joules strictly of potential energy. If I'm only stretching a little bit, maybe halfway, or I'm compressing only halfway from the amplitude, right? So say that the amplitude is 10 meters, right? If I compress or stretch 5 meters, then I might have 50 joules of potential and 50 joules of kinetic, right? But the idea is that I must always have 100 joules. At all times, I must have 100 joules. Just the amount of energy dedicated, the amount of energy dedicated to different forms of energy will differ. So at another stage, I might have 70 joules of potential and 30 joules of kinetic, but the idea, once again, is that I must have 100. So your total energy is constant. It's just the types of energy that make up that total energy will differ based on what's going on. So if I'm maximally stretching or maximally compressing the spring at the amplitudes, then it's all spring potential energy. If I'm only sort of compressing, sort of stretching midway through, right, then I'll have a mix of both. And then if I'm not stretching or compressing at all, where x is equal to 0, right, where the thing is just sitting there chilling at equilibrium position, then half kx squared, which is my spring potential energy, x would be 0, then elastic potential energy or spring potential energy is 0 joules at equilibrium position, and then therefore all of my energy, once again, my total energy is conserved. So if I have to have that 100 joules, if I no longer have any joules dedicated to spring potential energy, I have to have those 100 joules come into play somehow. How do they come into play? Well, at equilibrium position, instead of having a mix of kinetic and potential, or all potential, it's all going to be kinetic at equilibrium position. Does that make sense? I just want to make sure, like, if you can give a thumbs up or say yes in the chat or unmute, whatever you want. Okay, so I see a thumbs up from Kimberly. Anybody else? Is it not making sense, or is it all right? All right, I see another thumbs up from Eric. Okay. I'll take that as a yes. Yeah, I can go ahead and write it here. Hope you guys can see me moving my screen, right? I just want to make sure so that it's not frozen. Okay. Yeah, so at equilibrium position, 100% kinetic, 0% potential energy. And equilibrium is the same thing as saying x equals 0, right? So this is because half kx squared is equal to that spring potential energy, and x equals 0, so spring potential energy, so spring potential energy is equal to 0 joules, right? So if I'm looking at E total equals K plus U, then that equals just K, because there's no U anymore. Now at amplitude or peaks, it's going to be 100% potential, 0% kinetic, right? Because when you're stretching or compressing by that maximum amount, you're holding it back, or you're pushing it in by that maximum amount, and you're not moving at all. If you're not moving, V is equal to 0. So kinetic is equal to half mv squared, right? That equals 0 joules. And your E total, K plus U, will just be equal to U then, because your K is 0, because you're not moving. So at equilibrium, at x equals 0, it's 100% kinetic, 0% potential, because you're not compressing at all. Half kx squared is equal to 0 joules, so your E total is just made up of kinetic. At your amplitude, or your peaks, you're not moving at all, you're keeping it stretched. It's all potential, 0 kinetic. So total energy is just made up of kinetic at that point. And then, like, anywhere in between, will be a mix of potential and kinetic. Make sense? Okay. Now, going back to part C, where we're looking at the total energy at equilibrium, like I said, if you're at equilibrium, your total energy is kinetic, and you must have that same 0.25 joules from the beginning where you were at the peak. So that 0.25 joules is going from all potential to all kinetic now. So 0.25 joules is equal to half mv squared, where m is 2 kilograms, and then we're looking to find out what v squared is, right? So if we do that, we should get what for our v squared? 0.5, right? 0.5 meters per second. So v is equal to 0.5 meters per second. Make sense for the speed there? All right. Now part D is asking at what position is the potential energy of the oscillator equal to its kinetic energy? So what position is the potential equal to kinetic? So think about it, right? If I said that E total is equal to 0.25 joules, there must always be 0.25 joules. Then in order for kinetic and potential to have the same amount of energy, what would they each have to be to equal 0.25? Exactly, right? So they each should be 0.125 joules plus 0.125 joules to give me a total of 0.25 joules, right? So that's what I said, like where you have a mix of kinetic and potential at a specific point. Am I frozen? Oh, gotcha. Okay. Yeah, so I should have a mix of kinetic and potential somewhere in between, and that somewhere in between is exactly the position that we're looking for, right? So I know that my potential is equal to 0.125, right? Because like I said, they said, what position is the potential energy equal to its kinetic? Well, potential energy, this is kinetic. Potential energy is 0.125 and kinetic is 0.125 because they will be exactly equal to each other, which will give us that total energy value that must be conserved of 0.25 joules. So when spring potential energy is 0.125, what is the position, right? So we know that spring potential energy is half kx squared. So if U is 0.125 joules, right, then half times 200 newtons per meter. And then we're just solving for, am I frozen again? Okay. Yeah, so half times 200 newtons per meter times x squared to figure out our x. Now, we can't do the same thing with kinetic because kinetic energy doesn't have a value of distance, right? It only has a value of velocity or speed, half mv squared. So we can't really relate 0.125 to a specific position away. But we can use the idea that spring potential energy is half kx squared. So if we have 0.125 joules as our spring potential energy, we can set it equal to the spring potential energy equation and solve for x. Once again, the reason that we're using 0.125 is that they told us that the potential energy has to be equal to kinetic. Well, we know that potential energy must be equal to kinetic, but at the same time, we know that the sum of those two types of energies must be equal to the total energy at all times, right? So I must conserve that 0.25. The way I get that 0.25 will differ. So we said at 0, at equilibrium, it's going to be all kinetic. So I'd have 0.25 joules of kinetic energy. At the amplitude, or at the peaks, at the maximum compression or stretching distance, it's all potential. So I'd have 0.25 joules of just potential energy, of just U. But anywhere in between, at that distance that we're looking for, will be a mix of U and K. So they told us that U and K are actually equal to each other, right? So 0.25 joules is equal to K plus U, but K is equal to U and U is equal to K. So if we say K is equal to U, right, then we can just say that, okay, well, K is equal to U, so U plus U is equal to 2U, and that's equal to 0.25 joules. And so then we're solving for U. And so if you do that, 0.25 divided by 2, you should get U is equal to 0.125. And since we know that U is equal to K, like they told us in the problem, potential energy is equal to kinetic, then K is also equal to 0.125. And so you can see 0.125 plus 0.125, that gives us 0.25 joules. That's the energy conserved. And then we can use this equation here to figure out the exact distance away that would give us that type of energy, or that amount of energy, that energy combination, basically. So at that point, X should then be equal to 0.035 meters, I believe. Please correct me if I'm wrong on that one. Let me actually double check just so we're sure. Yep, 0.035. All right, so that's part D. Now we have part E, determine the magnitude of the acceleration at x equals a over 2. So, acceleration. Yeah, go ahead, Matthew. My first. Yeah, here's the answer. That's 0.035 meters. Oh, am I frozen again? Hold up. I really don't understand this frozen stuff, man. Like, this doesn't make sense. Like, I can perfectly stream movies, I can play Call of Duty if I want to, but I can't, like, teach you guys physics. It doesn't make sense. Right, hopefully you can see that now, right? Alright, cool. Part E is determining the magnitude of the acceleration. So if we're looking at acceleration, right, at a specific distance away, well, A is, once again, is the amplitude, right? So half the amplitude, we want to figure out the acceleration at that point, right? So we know that the amplitude is 0.05 meters, right? Well, let's first figure out what this distance is. So the amplitude is 0.05 meters. X equals 0.05 meters divided by 2. Well, then X should just simply be equal to 0.025 meters, right? Darn it. Frozen again. It's like I don't get a chance to, like, write down. I haven't written anything down yet. Like, all right, there we go. Hope you guys can see that. 0.025 meters. So that's our X distance that we're trying to figure out the acceleration at, right? So we know that they already gave us a hint here, but they said F equals ma, right? So F is equal to ma, and we're trying to isolate to figure out A, right? So A, that acceleration, is equal to force divided by mass. So we have the mass, that's 2 kilograms. Well, what force is in question here? What force are we looking at when we're stretching and compressing a spring, not a string? Spring force, right? So FSP. What is spring force equal to, Eric? Excellent, yep, negative kx, right? And in this case, you know, once we figure things out, we could get an acceleration that's negative, and that's perfectly fine, and that's accurate. But they're asking us for the magnitude. So essentially we can just take the absolute value of this, and so that negative sign will just basically be irrelevant at this point. So equals kx over m, right? So we have that x distance now of 0.025 meters, so let's just plug and chug again. So 200 newtons per meter for our spring constant times 0.025 meters for our distance away, which is half the amplitude, a over 2, and then divided by the mass, which is 2 kilograms, right? So that should just give us an acceleration value of 2.5 meters per second squared. Let me double check if that's right as well. Go ahead. Yep, you can do that. You can do negative kx, and then you get negative 2.5, and then take the absolute value just to show that we're looking for the magnitude. So yep, that's absolutely fine as well. So that's our acceleration for part E. Part F, it's saying that assume the oscillator is maximally stretched at t equals 0. Now, what does that mean? What does it mean when we say maximally stretched? What would be the distance there? Or how do we define that? Am I frozen again? Wait, can you see me moving the screen? Because I haven't written anything down yet. Oh, man. Oh, man. All right, here we go. So it says assume the oscillator is maximally stretched. So what does maximally stretched mean? I see someone in chat. Okay, yeah, never mind. The answer for E should be 2.5 meters per second squared, not newtons, because we're looking for the acceleration, right? But yeah. When we're saying maximally stretched, what do we mean when we say maximally stretched? What does that stretching distance correspond to, or how do we define it, basically? Let me see if I'm. Oh, okay. Let me see if I can call on someone, because Eric and Anna, you've been very active as well. So I just want to give someone else a chance, just because I want to make sure everybody else is involved. Let's go, Carlos. So when we say maximally stretched, what do we mean when we say maximally stretched? Like, what does that correspond to? The maximum stretching or compressing distance? And anybody else as well, like Carlos, if you're not 100% sure, no worries. So I see here, you said distance from equilibrium. So what distance exactly away from equilibrium? Because it's a specific distance when we say maximum stretch. Yeah, I mean, a distance away from the equilibrium, right? But specifically, like, if we were to assign a specific value for it, like if I told you, like on a graph, for example, right? If I were to draw a graph and I was like, okay, oops. I was like, here's the graph here, right? And these are all distances away. Like, this is the x, this is time, right? So if I were to tell you, okay, this is 10 meters, this is 5, this is 0 here, this is -10, this is 8. Yep, exactly, there we go. I'm just looking for the word amplitude. maybe I should have like asked it a different way. I'm sorry for like, yeah. No, no worries. Yeah, so yeah, it's amplitude is what we're looking for, the maximum stretching or compressing distance away. And so now they're asking what time will the oscillator first reach the position x equals a divided by 2. So half the amplitude, half the distance away from the amplitude, right? So we're looking at what time will we achieve that distance. So they already gave us a hint on how to solve this. X of t is equal to a cosine times, or a cosine of omega t, right? So basically, we're wanting to look for this position here, x equals a over 2, right? And at what time do we achieve that specific distance? So x of t is equal to a over 2. We already figured out what a over 2 is from before. That's the 0.05 meters divided by 2, which is the 0.025 meters, right? So if we say x of t is equal to a cosine omega t, then x of t is equal to that a over 2, which is that 0.025 meters. Our amplitude is 0.05. Actually, you know what? Maybe it's just a little bit easier to use the variables. So we know that x of t, the distance that we're looking at, is half the amplitude, a over 2, right? And this is a cosine omega t, right? Well, a will cancel out with a, because if you divide the a over, they'll cancel out. And so then you're just left with 1/2 is equal to cosine omega t, right? So how can we basically isolate for just the t time here to figure out at what time do we achieve this distance of half the amplitude, or a divided by 2? Yep, you take inverse cosine or arc cosine right at both sides. So if you, that function on your calculator, it'll either look like cosine to the -1, or it'll say arc cosine, either one, depending on your calculator. But cosine, inverse cosine of 1/2, and then inverse cosine of cosine omega t will cancel the cosine out. So then you're just left with omega t is equal to cosine, inverse cosine of 1/2, right? So this omega, right, this angular frequency, we actually figured this out at the very beginning. Remember, it was at 10 radians per second. We figured out when we never used it again. But now we're using it at the very end. We know that that's 10 radians per second, right? Times is t. So then we're just solving for t. So if we take that inverse cosine of 1/2 and divide it by 10 radians per second, we should get a time of 0.105 seconds. And make sure when you're taking the inverse cosine of 1/2 that your calculator is in radians. Otherwise, if it's in degrees, you'll get a wrong answer. So you take inverse cosine of 1/2 while your calculator is in radians, and then divide by 10 radians per second, and then that should give you a time of 0.105 seconds. So here, you're taking inverse cosine of both sides. So if you take inverse cosine of cosine, so like inverse cosine of cosine, that'll cancel out the cosine. And so then you're just left with what's inside the original cosine. So if you take inverse cosine of omega t, it just leaves you with omega t. Like whatever was originally inside the cosine, if you take the inverse cosine of that cosine, you're just left with whatever was inside of the parentheses for the original cosine function. Does that make sense? Yep. No worries. So, are you good up to here? The half equals cosine omega t. So we have the half equals cosine omega t. So now if we're wanting to isolate for t, if we're wanting to get t alone, the only way we can do that is by getting rid of this cosine. The way to get rid of cosine, the way to get rid of the cosine function is to take the inverse cosine, right? So for example, if you were to plug in on your calculator, if you just plug in like cosine to the negative one, well, it's not actually cosine to the negative one, it's inverse cosine, right? That's a different function. So if you were to take inverse cosine of cosine, let's say like 2 pi or something, you're going to end up with 2 pi as your answer. So in order to get rid of this cosine function to where that we can get to just omega t, and afterwards we can get t alone by itself, we want to take the inverse cosine. If you take inverse cosine of a cosine function, cosine of x, right, this will end up canceling out the cosine function, and you're just left with what was inside the parentheses for the original cosine function. So if I had, like I said, if I had cosine, inverse cosine of cosine 2 pi, if I plug this into my calculator, I get 2 pi. So that inverse cosine function cancels out the cosine, and it gives me whatever was inside the parentheses for the original function, right? So when I do that here on the right-hand side, inverse cosine of omega t, then that helps eliminate the cosine function, and it leaves me with what was inside the parentheses. So that leaves me with omega t. The thing is, when I take the inverse cosine of one side, I must take the inverse cosine of the other side. So then I take inverse cosine of 1/2. And so when I do that, I should get a value that's close to like 1.047. And then that's equal to omega t. And omega is the angular frequency that we found from part A, which is that 10 radians per second. So if I just divide by 10 radians, right, it's just dividing by 10, I should get a time of that 0.105 seconds. But the idea here is that we want to eliminate the cosine function and get what's inside the parentheses alone, to where that we can get this value here and divide by omega, and then we're left with t. The only way we can isolate for what's inside the parentheses is by taking the inverse of the trigonometric function. So this was sine omega t, right? I take inverse sine of that sine function, and that'll cancel out the sines, and it'll just leave me with omega t, right? And you can try this out with your calculator. If you have like sine, or if you take inverse sine of pi, right, the sines will cancel out, and you're just left with what was inside the original parentheses, right? So you're just left with pi. You can do the same with degrees as well. But does that make sense? Like the idea of using inverse sine to cancel out the cosine function and just get what's inside the original parentheses. Okay, cool. But that is part F there, and that's problem 1 all solved. Does that make sense for everyone else as well? The idea of taking inverse cosine there? All right, see a thumbs up. Awesome. So for problem 2, force and acceleration in simple harmonic motion, right? You have a 0.1 kilogram block attached to a spring that oscillates back and forth along a flat surface. Its displacement from the origin is given by x of t is equal to 12 centimeters cosine 2 pi t over 12 seconds, right? So they just gave us like this equation here, basically, right? And they gave us the mass of the block as well. So if they're asking for part A, what's the angular frequency? If I know that the original function, like the way it's set up, is a times cosine of wt, then if I look at this equation up here, what would my angular frequency, my fancy w, be? Exactly, right? Yep, exactly. So if I see here that it's cosine wt, right? Well, here's the t, so the rest of this must be the w, 2 pi over 12 seconds. So angular frequency is just equal to 2 pi over 12 seconds. So that's just merely just like analyzing the equation there. And so you can calculate that out basically, right? And you have your angular frequency, and that's what? That's like pi over 6, right? You can, I don't know if yeah, I think you should probably write out like the decimal value, because you could say like pi over 6 radians per second, but I would say calculate it out, and so you get 0.52 radians per second. And you can actually estimate it too. So if you think about it, like pi over 6, pi is roughly 3 divided by 6, that's like 0.5, right? So that's our angular frequency. Now, for the magnitude of the maximum acceleration, they're basically asking about A max. So A max here, does anybody remember? Oh, am I frozen again? Okay, there we go. So they're asking us about the maximum acceleration of the block, right? So A max. Now, there's this, like, honestly, this is a plug and chug. So yeah, there we go. There's the equation for A max, right? So A max is equal to the amplitude times omega squared, right? So amplitude times our angular frequency squared is going to give us our maximum acceleration. So we have our amplitude based on the setup of the equation. We know that xt is equal to a cosine wt, right? So this must be the a here, that 12 centimeters. But we know that we have our acceleration in meters, right? And everything's in SI units, so 12 centimeters is 0.12 meters, right? And then for our angular frequency, we already said that was 0.52 radians per second. So we just take 0.52 radians per second, and then we square that, and that should give us 0.033 meters per second squared for our maximum acceleration. Very, very simple plug and chug there. And then finally for the maximum force, right? So if we're looking at like maximum force, then that exerts a maximum acceleration there. Maximum acceleration, right? So we already have our maximum acceleration from part B. We have the mass of the block in the problem, so this is a simple plug and chug again. 0.1 kilogram times 0.033 meters per second squared, and then that leaves us with 0.0033 newtons. I think this is by far the easiest problem in all of physics that we've done so far. This is probably the quickest problem I've gotten through ever. But that's problem 2 there for force and acceleration in simple harmonic motion. Any questions about that at all? Nope, nothing. All right, fair enough. So problem 3, I think, is, yeah, this is the last problem, problem 3, energy in simple harmonic motion. So we have a block of mass m is attached to a massless spring with spring constant k and is set oscillating over a frictionless horizontal surface as shown in figure A. Figure B shows the block's kinetic energy, so this is a graph of the kinetic energy. So don't confuse this with spring potential. This is all kinetic here. This is a graph of the kinetic energy, right? Versus the position. When the block is at x equals plus or minus 5 centimeters, the kinetic energy is 6 joules, right? So part A now is asking what is the total energy in the oscillator? Well, if I'm looking at, or I want to figure out E total, right? So let me get 3 people to remind us of the different combinations of energy for energy total. So obviously we know that energy must be conserved, right? There's 3 different positions that I talked about in the energies at each position. So I talked about at the amplitude, at the equilibrium position, and then anywhere in between. So can I get 3 people that that haven't spoken up before during this session to tell us what the energies are at each specific point? So at amplitude, what's the energy composition? What is the total energy made up of? Is it made up of only kinetic, only potential, a mix of both? What's going on? And then at equilibrium position, right? And also at anywhere in between, basically. So I know Anna, you've spoken up. Eric, you've spoken up. Kimberly, you've spoken up. Matthew, you've spoken up. So Carlos, I think you've been pretty active, yeah. So, but I don't know if you had answered that question from before. Was this similar? Was this similar situation to this one? So you might be in the game for this one as well. I'm not sure whose iPhone, but you're in the game as well, and Zahar as well. I think you're in the game too. So, any one of you guys, I think that's 1, 2, 3. Oh, and then Muhammad as well. But I think you provided an equation once. So yeah, you can be in the game as well if you want. But you study physics with me at home, so maybe give someone else a shot. So Carlos, what would be at 0? At equilibrium, what is at 0? Is the kinetic energy at 0? Is the potential at 0? What's going on? Yep. So the potential is at 0, but are you asking or are you a little bit unsure what's going on? Potential is 0 at that point. That's absolutely correct. I'm just saying that, but do you understand why potential is at 0, or potential is 0 at equilibrium? So if you're at x equals 0, why would potential be 0? So remember, potential energy is half kx squared, right? So if x equal to 0, then potential should be equal to 0, right? So that's absolutely correct. Then at that equilibrium position, you're at a position of x equals 0. And so if x equals 0, our potential energy should be equal to 0 as well, because half kx squared, x equals 0, so potential energy is equal to 0. But then, what is our energy made up of then? If it's not made up of potential, it's made up of what? Kinetic, right? So at equilibrium, it should be all kinetic. Okay, so that's Carlos down in the game. Who else? Zahra is still in the game. I'm not sure who iPhone is, but they're in the game as well. So feel free to just shout it out if you want to unmute or type it in the chat. Just like whichever one. You don't have to go like one at a time. You can just like let me know what you think, and then like I can take each bit and analyze if there's any wrong answers and stuff. So I see at amplitude, it's all kinetic energy. Yep, so whoever iPhone is, thank you for the answer. But at amplitude, would it be all kinetic energy? So remember amplitude is the maximum stretching or compressing distance. So if you're stretching it and compressing it all the way, would you have any kinetic energy at that point? Like if you're holding it, right? If you're stretching it all the way to that maximum distance, or are you compressing it all the way? Would you be moving, would that block essentially be at motion at that maximum compression or stretching distance? It would just be potential, right? So they should all just be potential, 100% potential. So remember, at the peaks, remember I said here, well, actually I don't want to go because then I'll give the answer away for the last one, but for your amplitude, your potential energy at that point, right, or your E total would actually be made up of all potential, all potential, no kinetic, and that's equal to half k a squared, remember? At the amplitude, all of the energy is potential, right? So at the amplitude, at your peaks on your graph, you would see everything as potential, no kinetic. Now, anywhere in between, what would it be? I think there's only one person left, so Zahra, I think this is all you then. Or Muhammad as well, like if you guys just want to like answer at the same time. I don't know. I don't know how that'll work. So a mix of both. Yep. So a mix of both. Of kinetic and potential, anywhere in between. Right? So that's just the concept there, the idea there for the energy. Now, if I'm asking about the total energy of the oscillator, if this is a graph of the kinetic energy at a distance of -10, -5, 0, 5, and 10, right? X equal to 0, what is this defined as? What is the x equals 0 position? What do we call that? And imagine this is the like distance compressing or stretching. So at 0, not quite, right? Because at 0, that would be like, imagine if like these are the distances that I'm stretching or compressing away. So if I'm not stretching at all, what would this be, Matthew? exactly, right? Equilibrium position. I see some people already said it in the chat as well, equilibrium position. So at x equals 0, that's your equilibrium position. So that's the equilibrium position there, right? So remember what we said about equilibrium position. It's all going to be kinetic. Whatever energy you have, it's all kinetic. And then that's going to be the total energy. So if this is a graph of kinetic energy, right? At x equals 0, what is the kinetic energy here? Well, we can look at it. I think they said at plus or minus 5, it's 6 joules. So if this is going by, what is this? So this is 6 right here. So this is 1, 2, 3, 4, 5. Okay, so it's just simply counting by ones. So this is 6 joules right here. So 7, 8, right? So at the top here, we should see total energy, E total, is equal to 8 joules, right? Because at equilibrium, all of the energy is kinetic, none potential, right? Because potential is equal to half kx squared, and x is equal to 0 at the equilibrium position. So we don't have any potential energy. It's all going to be kinetic. And whatever the amount of energy that kinetic is, that's going to be equal to the total energy. So if at x equals 0, we have 8 joules of energy, that 8 joules of energy, that 8 joules of kinetic energy is going to be the entirety of our energy for the entire system, right? So in this case, it's 8 joules of kinetic energy of K, right? But it's also 8 joules total, right? Now, if I were to ask for part B, what is the potential energy stored in the spring when the mass is at x equals 5 centimeters? Well, at x equals 5, right, whether it be 5 or negative 5, they told us that it was at 6 joules, right? 6 joules of kinetic. How would I find out the potential? So I know E total is equal to 8 joules. How would I find out potential? And I know that kinetic is equal to 6 joules. So yes, so you have your total energy is 8 joules, right? And then your total energy is equal to K plus U. And if K is 6 joules, right, is 6 joules plus U, that's a horrible 6. 6 joules plus U, right, then U is equal to 2 joules. Now, Carlos, when you were saying half Ka squared to figure out what U is, right, well, that's going to be the amount of potential energy at the amplitude. So U is equal to half Ka squared, right? A would be the amplitude, which is here's 10 or negative 10, right? So if I were to plug that in, right, I would get that same total 8 joules, right? At the amplitude, remember, at the amplitude, it's 100% potential. Once again, at any of these points, energy total must be conserved, and it must be the same, right? So I must have the same 8 joules throughout. The way I get those 8 joules will differ. At the equilibrium position, at equilibrium, it's 100% kinetic. So if this graph shows that 8 joules of kinetic energy at the equilibrium position, then 8 joules of kinetic energy just so happen to be also 8 joules total energy in the system. If I'm looking at the amplitudes, right, at negative 10 or 10, well, I see 0 kinetic energy here. 0 joules of kinetic energy, 0 joules of kinetic energy there. Well, what does that mean? Well, that's because I'm at the amplitude, I'm at the maximum, I'm at the peak, maximum stretching, maximum compression distance. So 100% potential, 0 kinetic. So I see 0 joules of kinetic here, 0 joules of kinetic there. Well, I must have E total be the same, 8 joules throughout. So if I have 0 joules of kinetic, I must have 8 joules of potential. And so if I were to use this equation, half Ka squared, then the U would be equal to that 8 joules. I would plug in 10 for A, 10 centimeters, right, or 0.1 meters. But the issue here, once again, is that I don't have K, right? They never gave me the value of K. So even if I wanted to, I couldn't use this equation. And at the same time, it's not a valid equation to use because this would give me basically the potential energy at x equals 10 centimeters, not x equals 5. And even if I said u equals half kx squared, so like some distance like 5 centimeters, right? If I plug that in, then yes, I could use that equation. That's perfectly fine. If I plugged in 5 centimeters, squared it, multiplied by my k, multiplied by 1/2, or 0.05 meters essentially, not 5 centimeters, then I could figure out that way as well. But the issue is that I don't have the spring constant value available, so I can't calculate it that way. But what I do have is that knowledge of that the total energy is made up of kinetic and potential, right? If the total energy is 8 joules at that equilibrium position, it's made up of only kinetic, right? But what if it's at 5 centimeters here, right? Then I'm no longer all kinetic, okay? I'm only a little bit kinetic, and then so this will be the amount of kinetic that you have, and then this little difference between the total and the graph would be my spring potential energy, right? So another way you can think about this is that your height from the x-axis to the graph itself will give you the kinetic energy, and then from like the maximum point here of the kinetic, if you just move downwards like that, that'll give you the amount of potential energy, right? So if I go from here to here, from x-axis to the graph itself, I get 6 joules of kinetic. If I go from the top here, where my maximum is at, then I go 1, 2 joules of potential. So, yeah. Does that make sense, Carlos, as well? Yep, exactly. I just want to make sure, Carlos, are you okay with that information so far? Does that make sense? Okay, awesome. So for the spring constant, right, we can use that spring potential energy now, which is that half kx squared, right? And then the only value of spring potential energy that we know is that value that we calculated from B, which is that 2 joules. So we set this equal to 2 joules, and we know the x distance is 5 centimeters, then we can solve for k. So half times k times that 5 centimeters, which is 0.05 meters, square it, is equal to 2 joules, and then we solve for k, right? And that k should be 1600 newtons per meter. Sound good for the spring constant so far? All right, cool. Part D. It's telling us that the maximum acceleration of the block is 40 meters per second squared. What is the mass of the block? So they're giving us A max is equal to 40 meters per second squared, right? Now they want to figure out the mass. Well, how can I relate maximum acceleration to mass? That's the big issue here, right? So there's one way that comes to mind immediately for me, just based on the fact that they're telling us maximum acceleration. There might be another way, but I'm not sure if it gives us the right answer, if it's the correct way to go about thinking about things. But anybody have any suggestions as to how to approach solving for the mass here, if they're giving us maximum acceleration? Or can we start? Wait, can you say that again? Because you got out at the in the middle there. So you're saying A max is equal to what? Negative K? Oh, like that? So that's actually perfect, I'm pretty sure. Mm-hmm. So yeah, that's right. And let me actually derive how we get to the K over M times X part. So we know that A max is equal to A, like at least from the slides, right? So it's the amplitude times the omega squared, right? So omega is equal to root K over M. So if we square a square root, we just get whatever is inside the square root, right? So A times K over M in that case, right? So we can just use A, the amplitude of 10 centimeters, right, or 0.1 meters, and then multiply by our spring constant and divide by the mass. Multiply the mass over the divide by the acceleration till we get the mass. That's what I meant. So that's a way of doing it. The other way I'm considering, but I'm not sure if it's quite right, is that if you have like F max is equal to, like if we're looking at like a spring, right? There's the spring force, so kx, right? And then the F max is equal to M A max, kx like that. And so then your A max is equal to kx over M. So that's basically the same thing. And then your x distance that you use, right, will just be like your amplitude in that case, which is at 10 centimeters. So I think that actually works out perfectly as well. So either way, I think you can do it, but I would probably prefer to start with this like maximum acceleration equation here and then go from there. Because if you have omega squared, omega is equal to root K over M. If you square them, that gets rid of the square roots, and so you're just left with A times K over M. And so your A here's your amplitude. But yeah. And so you just plug in 0.1 meters. You just move this over here. 0.1 meters times that 1600 newtons per meter, and then divided by the mass, right? Or at least we multiply the mass over and then divide by the acceleration. So just do that, equals A max. And then let me just make everything a little bit smaller here. So A max, actually, my bad. 0.1 meters times 1600 newtons per meter divided by 40 meters per second squared will give us the mass. And so then the mass is just equal to 4 kilograms. So that would be the mass of the block using that maximum acceleration there. Yeah, so here the amplitude is 0.1 meters, right, or that 10 centimeters, because at negative 10 or 10, right, whether you go positive distance or negative distance, right, your kinetic energy is 0, and your kinetic energy is completely 0 when you're at the amplitude, because at that point you're going to be at 100% potential. Does that make sense? Yeah, so at your amplitudes, right, negative 10 or 10, those points are where you're going to have K is equal to 0 joules. So you have no kinetic energy whatsoever when you're at the amplitude. That's because you have 100% potential at the amplitude. 100% potential, 0 kinetic, right? And so 0 kinetic occurs at negative 10 and 10 centimeters respectively, which is that 0.1 meters that I was looking at. Yeah, so for the amplitude, right, for when we're calculating the maximum acceleration, right, there's an equation for maximum acceleration, which is the amplitude times the angular frequency squared, right? And so based on that relationship here, if we can get that amplitude from the graph and then multiply it by the angular frequency squared, we should be able to get that maximum acceleration. But what we're looking for here is the mass of the block. And so the angular frequency is a function of the square root of the spring constant divided by the mass. And so if we can just plug this in here, the angular frequency, and square it, right? So if we square root K over M, square that, right? Because that'll just be omega squared. Then we're left with K over M. And then that's multiplied by our amplitude. And so our amplitude from the graph, we figured that out to be 0.1 meters. And if we just multiply by the spring constant, divide by the mass, that gives us our maximum acceleration. And then if we rearrange the equation to figure out for the mass, that's how we can do it. The main relationship is the fact that your angular frequency, your speed, right, is dependent on the mass of the block, right? And so if, for example, you were to have a heavier block, you'd be going at a lower angular frequency, right? If we were to increase the denominator here, if we were to increase mass, that goes up, then your angular frequency goes down. So think about like the heavier an object is, the slower it kind of moves, right? With regards to its angular frequency, right? In this relationship here. And so maximum acceleration will then depend on, because think about like just in general, like acceleration and velocity. Like acceleration is dependent on velocity in the sense that acceleration is the change in velocity over time, right? So there's a relationship between velocity and acceleration. Now, in this case, for the acceleration like of a spring block system, right? That maximum acceleration is figured out using this equation, and then the angular frequency, that angular speed basically, will help us determine the maximum acceleration, and that angular speed is determined or is dependent on the mass, right? And it's once we have that mass, right, that we figured out here, well, we have that mass. And so that maximum acceleration, like I said, is just going to be dependent on the amplitude and the angular frequency squared. But in order to get that amplitude, we have to analyze the graph here and realize that the amplitude is the point at which you have 100% potential energy, 0% kinetic. So we look at where the graph is 0 for kinetic energy, and that's at negative 10 and 10 centimeters, right? So that's why the amplitude is 0.1 meters or 10 centimeters, right? And then using that equation, A max is equal to A omega squared, right? We have our maximum acceleration. We figured out the amplitude from the graph. And then the omega, like I said, is dependent on the mass and the spring constant. So we have that spring constant, and now we're trying to figure out the mass. But yeah, that's pretty much it with regards to that relationship there. But does that kind of clear things up a little bit? Yeah. Mm-hmm. Zero kinetic energy at the amplitude. It's all 100% potential. Because like imagine, in order to like stretch that spring to its maximum distance, imagine yourself just pulling it that distance, right? So if you're pulling it or you're compressing it all the way, you're holding it there. Imagine like trying to hold it in that position because it's essentially trying to get back to equilibrium, right? It's trying to get back to where it was. So if you're holding it, compressing it, stretching it to that maximum distance, you're really like tugging on it, you're really pushing on it, but there's no physical motion of like the spring or the block system at all because you're holding it there. So when it's maximally compressed or maximally stretched, you have all potential in zero kinetic. And also, if you think about it, like even if you let that spring go and it starts moving, it oscillates between that those two amplitudes, right? Between -10 and 10. And so you kind of like if you were to really slow this down, you look at slow motion, right? Then you would kind of see that once it kind of moves all the way to the right, right? This is basically how it looks like. So if I have this spring and I compress it to this distance, right? And here's the equilibrium and here's the maximum distance, right? So this is 0 and this is amplitude positive and this is amplitude negative, right? So once I'm compressing it, right? So once I let it go, it's gonna shoot back this way, right? And so when it shoots back to the right, what you see essentially is it moves really, really fast, and then like once it hits that maximum amplitude, it goes basically like this. It goes like that. So it kind of moves, and then it kind of hits this point where it's like, all right, let's go back. So it goes, and then it's like, okay, hold up. Now we get to this maximum amplitude. It's 0 now. 0 kinetic, no motion, all potential, and then all of a sudden it just moves back, right? It springs back the other way to the equilibrium position. And that's also kind of the idea if you think about throwing a ball all the way up in the air, right? So if I launch a ball up in the air, what happens is it goes up and up, right? And then once it hits that maximum vertical height, right, you see it kind of go, and then it kind of slows down and then comes back down, right? So it goes up, slows down, and it comes back down, right? So at each respective amplitude, right, left or right, whether I'm compressing or stretching, the idea is that it goes, all right, I'm stretching, and then all of a sudden I come back, right? So once it hits that little, like right before the turn, basically, like if we think about it as turning, right? So once it hits the little maximum position, the maximum amplitude, at that point, the block is like not moving anymore, and then all of a sudden it kind of like shoots back, right? So once it hits that amplitude, whether positive amplitude or negative amplitude, at -10 centimeters or positive 10 centimeters, when it reaches that maximum compression or stretching distance, if you really like were to film it and slow it down, you'd see it stretch all the way, kind of slow down up until it reaches the amplitude. Now it has effectively no motion, no velocity, and then all of a sudden shoots back again, right? And once it shoots back, once it hits that compression distance, the maximum compression distance at negative amplitude, right? And then it kind of shoots back to the right again, right? So I don't know what the best like real life example to show this would be, but honestly the best thing to kind of describe it also is just the, shooting a ball upward example. So if I just launch a ball upwards in the air, it goes up, it slows down, right? Because you launched it with a certain velocity. Then due to gravity, the velocity of the ball starts to decrease. And then all of a sudden, don't you kind of see the ball kind of like hang in the air, basically? That hanging in the air is the same as what happens basically at the at the amplitudes, right? So at that point, the ball kind of hangs in the air, or that point at that amplitude, the spring or the block system, right, will kind of hang in position with no velocity at all and then shoot back, right? Or essentially, if we're looking at the ball, once it hangs in the air for like a split second, it's going to come back down again due to gravity. So if I stretch it, and then I let it go, well, it's going to shoot back to the left, right? So if I stretch it this way and I let go, it's going to shoot back to the left up until it compresses to that maximum distance. And then it's going to hang at that maximum distance for a very split second, and then it's going to shoot back again to the right. And then it's going to stretch to the right again once it hits that maximum amplitude, and then it's going to hang there for a split second and then move back to the left. So it's going to oscillate. And that's what happens on the graph where you see this is x versus time, right? I stretch. I hit that maximum position, I hang in the air, and then I come back down to that equilibrium position. And then I go all the way back, right, to that amplitude. I hang there for a split second, and then I move back up, right? So it kind of goes hang in the air, then come back down, hang, and then I come back down, like that. So it's a matter of like stretching, I hang, and then I come back down. Compressing, I hang, and I come back up. Stretching, I hang, and then I come back down, like that. And so that's kind of what's going on there. So at the amplitude, that's why you would see 100% potential, because at that point it kind of hangs. It pauses essentially for a split second. That's where you have zero kinetic energy. And it's all potential, because at that point, it's either stretched or compressed by a certain distance by that maximum amplitude, and it hangs there at a split second, no motion, and that's why there's zero kinetic, right? At equilibrium, so I imagine like if I'm moving back towards equilibrium, right? So if I go upwards, hit that amplitude, I come back down. At equilibrium here, right? At this x equals 0 point, I see my maximum speed, right? I see all of my energy now being kinetic. Because if I started off here, the spring is completely relaxed. If I move to the right, move to the left, that's going to give me some spring potential energy, some kinetic, whatever, right? But once I hit this original position, I'm no longer technically compressed based on my original position. So that's when I see, if I look at half kx squared, I see no compression, because I came back to the original position, x equals 0, no compression, and no stretching, but I must have the same total energy throughout. And so at that point, instead of being some potential, some kinetic, or all potential, it's going to be all kinetic at that point. I'll reach my maximum speed at the equilibrium position. And so that's why E total at equilibrium, right, it's going to be K. That's half mv max squared. Does that make sense? Okay, awesome. So E, what is the angular frequency of the system, right? So they're just asking for the W here, right? So that's, we kind of wrote that out earlier here, right? Root K over M. So if we were just to figure out that specific component alone, well, that's root 1600 divided by the mass, which is 4 kilograms, right? And that gives us 20 radians per second for our angular frequency. Now, part F, where it's asking how long does it take to complete one oscillation, what is this defined as? The time it takes to complete one oscillation. So I see, Carlos, you asked, can you use hertz as units? You mean for part E? No. For angular frequency, it's only in radians per second. For frequency, just for frequency, that can be in hertz, right? So that'll be like, if you said 3600 hertz, that's like saying 3600 cycles per second, right? And so that's why hertz are seconds to the -1, because your seconds would be in the denominator, right? but since omega is 2 pi times the frequency, it's like the radians per second, right? But yeah. And then what is this defined as? The time for one cycle or one oscillation. What do we call that? Period, right? So this is our period, the time it takes for one cycle. And so if we have omega, we know that that's equal to 2 pi f, or that's the same as 2 pi over period. So this is just a matter of rearranging equations and plugging and chugging. 2 radians per second, not 20 radians per second is equal to 2 pi divided by t. And we can rearrange to take t is equal to 2 pi over 20 radians per second. And so then we get 0.314 seconds as our period there. Why would we have to multiply by 2? Oh, I see what you mean. So like you're saying like, so from like, yeah. Yeah, so that 0.314 seconds will actually cover that entirety, because that'll be one whole oscillation there, right? Yeah. So you don't have to multiply by 2 at all. Nope. Because think about it, like I started from equilibrium, I come to the amplitude, right? I come back down to that negative amplitude, and then I come back up. So that's one whole cycle there. Does that make sense? But yeah, that's one whole cycle there. So like from equilibrium, or from starting position to the maximum, back down to the equilibrium, down to the negative maximum, or well, to the minimum then in that case, that -10, and then back up to the equilibrium, right? So it's like saying, okay, I started off at 0, I stretched, I came back, I compressed, I came back. So that kind of almost like forms a circle there, right? So you see if I start at 0, I stretch, I come back to the 0, I compress, and then I come back, right? So you can see there, that kind of forms a circle basically. Make sense? Okay, awesome. Now that is problem 3. Any questions at all about this stuff? Is it all kind of making sense, the idea? Like hopefully this little area here also helped out a lot with the different stages, like what types of energies are made up, or at different points what is the energy composition basically. For 2b I got 0.033, yeah, 0.033, 0.032, about that range. Yep. But that's it for the written homework for this week. Like I said, we'll have the exam review sessions here in the next couple of days. Let me just kind of like shout them out basically to the people that are going to be watching this online. But basically we're going to have Tuesday, November 29th from 1 to 4 p.m. That's weeks 10 and 11 review. Wednesday, November 30th from 1 to 4 p.m. weeks 12 and 13 review. And then, what is it? Friday, December 2nd. Yep, Friday, December 2nd from 12 to 3 p.m. That's weeks 14 and 15 review. And then finally, Wednesday, December 7th, the day of the exam, from 10 a.m. to 6 p.m. Just an open drop-in session. But yeah. So that has been it, I think, for this written homework. I'm probably going to go ahead and end the recording on that note, and then let me know if you guys have any other questions. If not, you're free to go. Like I said, hope you guys had a wonderful Thanksgiving break. Enjoyed it with family and friends, and happy Thanksgiving to those who are watching online as well. So hopefully see you guys soon.